This lesson deals with the VI characteristics of MOSFETs and their modeling. You can find these notes in the ECE302 ebook in Chapter 4, starting on page 12. What I've sketched out here is a more accurate representation of an N-channel enhancement MOSFET with a threshold voltage of 3 volts. I've also drawn the symbol here for the N-channel MOSFET, and I've shorted the bulk to the source pin. And I did this because when you buy a discrete MOSFET, this is done internally in most cases. There's a few where they'll actually give you the fourth terminal out. But in doing IC design, we do have to hook up this fourth terminal correctly, and you'll learn about this in IC design courses. The diode is between the bulk and the source is automatically not forward biased because there's a short circuit across it. We do have to worry about the diode from the bulk to the drain and making sure that that's not forward biased. We'll check for that in this chapter. I've also marked the ohmic region, the current saturation region, or just saturation region, the cutoff region. I've also marked the pinch-off parabola. Again, let's model these different regions. The simplest is in cutoff because the drain current is 0. Of course, the gate current is 0 because there's really an open circuit between the gate and the rest of the material. If you recall last time, we showed that in cutoff, the gate source and the gate drain were both less than or equal to threshold. Our model is going to be 0 current for the drain, the source, and the gate. So just open circuits. We can't guarantee the voltage across an open circuit, so we'll need to do the checks that the gate source is less than or equal to the threshold voltage, and the gate to drain is less than or equal to the threshold voltage. You may notice that this is very similar to the JFET, except that threshold's replacing pinch-off. That's going to continue on as we go through the modeling. Let's next take a look at the ohmic region. And we showed last time to be an ohmic, the gate source voltage was greater than threshold, and the gate to drain was greater than threshold. On the schematic up on top, just like with the JFET, the gate to drain voltage is the gate source minus the drain source. Well, the gate to drain is not on the VI characteristics, and so let's use this inequality and solve for, again, the drain source voltage like we did for the JFET. Putting this over here, we have the drain source voltage would be less than or equal to the gate source and then minus the threshold voltage. The drain current, when you're in the ohmic region, was found experimentally to be this expression, which is K times the quantity 2 times the quantity gate source voltage minus threshold times the drain source voltage and then minus the drain source squared. And you may notice that this is exactly the same equation we had for the JFET, except that we have threshold replacing the pinch-off. We're going to use a current source to represent this. Again, not as nice as the BJT. We've got a rather complicated expression for the current in terms of 2 voltages. And again, we have a voltage across the gate source and the gate to drain. We can't guarantee that that's any particular value because it's an open circuit, and that can be positive or negative or 0. So I have to check that the gate source and the gate drain are both greater than or equal to threshold. Let's next model a saturation region. If you recall from last time, we showed that the gate source voltage was greater than or equal to the threshold voltage, and the gate to drain was less than or equal to the threshold voltage when we were in saturation. Let's use our gate to drain voltage equation again to solve for the drain source voltage. From our schematic of the transistor, the gate to drain voltage is the gate source minus the drain source, and that needs to be less than or equal to the threshold voltage. Solving for VDS then, VDS needs to be greater than or equal to the gate source minus the threshold voltage. What this means is that when the drain source is greater than or equal to the gate source minus the threshold, we're in saturation. Let's see what that looks like on the VI characteristics on page 12. Let's take a gate source of 5. So we take the gate source minus the threshold, and it's 5 minus 3, we would get 2. Whenever the drain source is greater than or equal to 2, we're in saturation. So here's 2, and here's when we're greater than or equal to that. Let's try 6. We take a gate source minus the threshold of 6 minus 3, we get 3. Whenever the drain source is greater than or equal to 3, we're in current saturation, and that's going to be right down over here. If the inequality is the other way, if the drain source is less than or equal to the gate source minus the threshold, we're in the ohmic region. That's what's on the bottom of this page. Let's go back to page 13. The drain current was found experimentally to be the following expression for N-channel MOSFETs. It's K, same K as the previous model, times the quantity, the gate source voltage minus the threshold squared. We'll use a current source to model that. The voltage across the gate source and gate to drain is across an open circuit, so we'll need to check that the gate source is greater than or equal to threshold and the gate to drain voltage is less than or equal to threshold. So if we assume this model and we do this check and it's consistent, then we made the correct guess. We have transition points, they're marked with dots on the previous page, going from the ohmic to saturation region. We're going to again call that the edge of saturation. And so we're taking a look at the fact that the ohmic region and the saturation region have some commonality to them. They both have that the gate source is greater than or equal to threshold, but the gate to drain is greater than or equal to threshold for ohmic and then less than or equal to threshold for saturation. So we could take the equality as the overlapping case. And that'll be the case of the gate source minus the threshold equal to the drain source voltage. And this was found with the gate to drain equal to the threshold. We could use this expression or the previous one to evaluate this term that's here. We're going to plug in that this term is equal to the drain source voltage, and so we're going to just square it. That's going to give us that pinch-off parabola equation where I have a boundary between the ohmic and the saturation region as a parabolic equation. We're having the same equations that we had for the N-channel JFET, just that the threshold voltage is replacing the pinch-off voltage. All the other polarities and signs in the equations are the same. With the JFET, we had a case where the gate source was equal to 0. We used that to solve for K. We don't have that case now, so what we're going to do is just pick any point on the current saturation region, because it's the easiest of the two equations to work with, and just evaluate it at a point. On page 12, let me pick the gate source equal to 6, where the drain current was 4.5 milliamps where it leveled out. I can use this equation to solve for K. It's going to be the value of I sub d divided by the quantity gate source minus threshold squared. This was 4.5 milliamps. Gate source was 6, the threshold was 3, and it's going to give me 0.5 milliamps per volt squared. We'll also have an edge of cutoff, where the cutoff region and the saturation regions meet. It's going to be the same as we did for the JFET. The reason is that they both have the gate to drain is less than or equal to threshold, but in saturation this is greater than or equal to threshold, and in cutoff it's less than or equal to threshold. Let's take the equality case. Using the drain source equation here as being greater than or equal to the gate source minus the threshold, but the gate source equal to threshold, so it's greater than or equal to 0. So this is the line along the x-axis, just like we had for the JFET. Let's plot the transfer curve of I sub d versus VGS when we're in saturation. For that case, I sub d is equal to K times the quantity gate source voltage minus threshold squared. In our example, this was 0.5 milli, and the threshold was equal to 3. When the gate source equals 3 volts, we'll be at 0 current, and then we'll have a parabolic equation. There is another part to the parabola over here, but that part is 0 when we're doing the actual device. SPICE will have to deal with this in terms of solving its equations. We'll talk about that in a future video. From this curve, we can pick up the threshold voltage, and then we can pick up a value of K if we can record one of the values that are here, because we then solve for K. And these are usually provided in data sheets of transistors. If there's an N-channel MOSFET, we could find a P-channel MOSFET by using a piece of N-doped silicon and inducing a P-channel. I drew this upside down because in electronics we show current flowing from the top to the bottom of a schematic. And every voltage and every current is going to be reversed because we're replacing P material by N material by P material. The current is entering the source coming out of the drain. These two are equal to each other because the gate current is still 0. Now our voltage is between not the gate source but the source to gate, and the voltage across the source to drain, and the voltage across the drain to gate will be the parameters we're taking a look at. The curves will be identical to the N-channel case. If we do this, reverse all currents, reverse all voltages. The voltage reversal will be in the subscript, so this would give me the same results we had last time. For a threshold voltage of 3 volts, we would have an ohmic region, a saturation region, and a cutoff region. Also have a pinch-off parabola as the intersection of the ohmic region with the saturation region. If we do this, the threshold voltage will turn out to be positive. So just like the JFET, everything's identical for the P-channel device. Just simply change all the directions of current and change all the subscripts, and everything else will come out the same. That's not usually how you'll find this data in other textbooks, and so be aware of the fact that I'm defining this a little bit different. I'm doing this so that it's easier to remember. If we do this reversal of currents and the flipping of the subscripts, then all the inequalities stay the same. There are many, many textbooks where they don't do that, and the inequalities are actually just the opposite for P-channel devices. Extremely difficult, so I decided many years ago to go with a notation where all the equations are basically the same for the JFET and the MOSFET. So here too, in cutoff, it's now the source to gate and the drain to gate that are less than or equal to threshold, and the model's the same and the checks are the same. In ohmic, equations are the same, just simply the subscripts are changed. If you learn the equations for the N-channel JFET, it's the same equation here, it's just that thresholds are replacing pinch-off and we're flipping the subscripts. Likewise for saturation. Now the source to gate greater than or equal to threshold and the drain to gate less than or equal to threshold. The same equation when we're in current saturation. I didn't show the models for the cutoff, ohmic, and saturation regions for the P-channel MOSFET because they're the same as those on page 7 for the P-channel JFET. And the checks are the same if you replace the pinch-off voltage by the threshold voltage. Edge of saturation is the same with the same parabolic equation. Would use the same technique for solving for K. Just pick one value in current saturation and use that to solve for K. And lastly, there'd be an edge of cutoff with the same conditions we had previously, but now it's the source to drain is greater than or equal to 0. And again, it's the x-axis. There are a lot of inequalities to keep straight when dealing with FETs. Many years ago, I came up with a little trick, memory trick, that allowed me to draw an analogy between the BJTs and the FETs and the inequalities. The BJT and the FET are totally different transistors, but there is some similarity with their inequalities if you do the following. Let me go back and look at the BJT again. When we forward biased this at 0.7 and we saturated the output at 0.2, we didn't solve for the base collector voltage, but that diode's forward biased. Let's solve for it now. The rise in voltage would equal the drop of 0.7 minus 0.2. This would be 0.5 volts. Let me define that as the base collector turn-on voltage. Now think of these curves as exponential curves, where we've got basically a turn-on voltage, and then we can continue on beyond that. To be in cutoff, the base emitter and the base collector were not forward biased. They were below that turn-on voltage. To be in cutoff for an N-channel JFET or MOSFET, the gate source and the gate drain were less than or equal to either pinch-off or threshold. The inequalities go the same way. So just kind of think about the BJT not forward biasing those two diodes. Then to be in saturation, of course, we forward bias those two, and we're going to be greater than or equal to their turn-on voltages. And to be in the ohmic region, the gate to source and the gate to drain are greater than or equal to their values of pinch-off or threshold. So again, the inequalities go the same way. And then to be in the active region, which we call the saturation region or current saturation region for the FET, the base emitter is forward biased and the base collector is reverse biased, or not forward biased. Same is true here. We have greater than or equal to pinch-off or threshold, and then for the gate to drain less than or equal to pinch-off or threshold. Remembering this idea with the BJTs I find easy, and then I can just get these by just reasoning them out. The same is true for the P-channel devices if we just simply flip the subscripts. For the PNP, we now have the emitter base turn-on voltage and the collector base turn-on voltage. So when we're in cutoff, we're less than that forward biasing. And then to be in cutoff for the P-channel, it's now the source to gate or the drain to gate being less than or equal to pinch-off or threshold. For saturation, we're forward biasing both of these, the emitter base and the collector base diodes, and in the ohmic region, source to gate and the drain to gate are greater than or equal to pinch-off or threshold. And lastly, for active, we forward bias the emitter base diode, reverse bias the collector base diode. And now for the inequality here, we have the source to gate greater than and the drain to gate less than pinch-off or threshold. And these are the VI characteristics of MOSFETs and their modeling.